when writing it Japanese, that's probably the best way to go about it. Okay, oxidation numbers. Hopefully you should know. Elliot, do me a favor. Go hit the second light from the left, please. No, I'm really not. All right, oxidation number. If you can't do this, then there's no point in you even trying. Okay, MnO4. There's no point in you even trying. And, guys, it really is. It's easy. So set this equal to what? -1. Okay. What's oxygen in this case? -2. So that brings down to -8. So what does that make it? Manganese is +7. That's easy, 1-pointer. Okay. Then it says identify the reducing agent. Well, we always set this up. We always set up the ox and Ra and the red cat what? Oa. Well, which one goes to the oxidizing? Oh, we're looking for the reducing agent. So which one are we looking for? We are looking for the thing that is being oxidized. So oxidation is a what? Loss. So the value should go up. So this is going from a 2+ to a, well, there we go. We're done. It's iron. Okay? Does that make sense? Okay, very good question. If they're asking you for the oxidizing agent, it will not be hydrogen, and the reason why is because over here, hydrogen is also a +1. Okay? Now, and then it says if it was oxidized, now MnO4, we've said it's a +7. Well, over here, it's a what? +2. So that is being what? Reduced, therefore it's the oxidizing agent. Good question. So all you're doing is looking for which one is being oxidized. And again, it is, now, you would say iron 2. So the answer to B is Fe2+. It's not what it's turned into, it's what it is. Okay? That's it. You're done. So you would have earned 2 points thus far. And you're good to go. Okay? Now, I know C talks about color change, and we haven't really talked about color change a whole lot. The mass of the iron 2 compound is carefully measured before a sample is dissolved in distilled water. The resulting solution is acidified. The solution is titrated with permanganate until the endpoint is reached. Now, here's the deal. Permanganate is extremely this color. Okay? Let me show it to you. I want to show it to you. Joey, did you say it was purple? It's here. The question says the end point is reached. Now, whenever you do a titration, what happens is you drop color in, okay? And it's going to stay colorless until you have reached the end point. The end point is when you have this. Equilibrium. Okay? So you have literally reached the point at which you know the pH, you know the concentration of it. So describe the color change that occurs in the flask when the end point of the titration has been reached. Explain why the color of the solution changes at the end point. Okay? All right. So what's going to happen is it's going to go from clear, because that's the color of the solution, to pinkish purple. Was that in the video? Okay. All right. So it goes from clear to pinkish purple. That's what it's going to stay. I mean, all it says purple dash pink. It doesn't. You can say purple. You can say pink. It doesn't matter. Okay. So it's a very faint, light pinkish purple color. Pink, purple, purple, pink, whatever. What? Magenta would work. Yes, Elliot. Magenta will work. So then it says, explain why the color of the solution changes at the end point. Now, it's got a long paragraph. I'm just going to tell you what it says and then tell you what it means. At the end point, there is no iron 2 ion left in the flask to reduce the color permanganate. So essentially, this right here is this is a purple color. And when you drop it into this is essentially, this right here is clear. Okay, so when you drop things on top of each other that are ions, what are they naturally doing? or naturally neutralizing, right? Well, you're dropping this into a whole lot of that. So what is that? There's more ions in solution, right? So what is it able to do for every one of those that drops in? It eats that color up, right? So to the point at which finally there's more purple being dropped in than there is enough of the iron to eat it. Does that kind of make sense? All right. You have, hang on. You have this solution, and there are thousands of these things in there. Thousands of them. Okay? And then you have this titrant. Okay? And it's this deep purple color. Well, every time you drop one purple in, you're dropping an MnO4 minus. Well, how many of these do you need for every one of these for it to neutralize? Why is it 2, Joey? 2 plus, and that is 1 minus. So you need 2 of these for every one of those. So every time you drop, what's going to happen to one of those? Every time you drop 2 of these, what's going to happen to that? It's going to cancel, right? So eventually, what's going to happen to all the FEs? They're going to neutralize themselves out. So once you drop this purple color in there, is there any iron left there to neutralize it? So what's going to happen to that purple color? It's going to stay. Does that make sense? So there's not enough iron ions to neutralize that permanganate ion, which is that purple permanganate. Okay, you with me? Does that make sense? You're looking at me looking crazy. Taylor, do you get it? Then I'm moving on. All right. Let's see. Again, at the end point, there is no Fe ion left in the flash to reduce the colored permanganate ion. So a small amount of permanganate ion is added after the end point. The unreacted permanganate ion present in the solution colors it a faint pink or purple. So once you get rid of all of these and you keep dropping this in here, that is going to turn a faint purple color because there's nothing there to take away that purple color. Does that kind of make sense of what's going on? Okay. Going back to the questions. All right. D. Let the variables G, M, and V be defined as the following. G is the mass in grams of the sample of iron 2, M is the molarity, and V is the volume in liters added to reach the end point. See, this is where the number of moles of iron in the sample. What would you do? Where am I at? See, honestly, in terms of these variables, the number of moles of permanganate added to reach the end point of the titration is expressed as M times V. Because that's concentration times volume. How do we know that? Because that is what? Molarity equals, or moles equals molarity times volume. That should be easy. Using variables. Does that make sense?
So is that what we do for I?
Yeah, which is rather strange. But it says, but here's the deal. This is the number of moles of that. So if we want the number of moles of iron, this is what it says. Moles of Fe2+. Let me make sure. Now you're gonna know where this comes from. 5 moles of Fe2+ over 1 mole of Mn2O4. Where'd that come from? The coefficients, right? And for some reason, it then does this. No, it wouldn't, because basically it would be flipped. You see what I'm saying? We're starting with the end result on the back side. Which is weird. And I guess because they tell you to use this, they want that. But this, all it tells you is what? That tells you moles. Well, see, the thing is, you have to use these 3 things. So molarity times volume is...
So if we just put M times V, would that be right?
Yeah, that's what they want. That's how they have it. You couldn't use moles. All right, let me show you. All right. Okay. I'm with you on that, but let me.
Use a calculator.
Yeah, you can't use your calculator for so. They want moles of what? Moles of Fe2 plus. This is how we're used to doing it. Okay. Do they tell you how many moles of Mn2O4 you're starting with? No, but they tell you M and V. So molarity times volume of MnO4 minus. I have to get rid of this. Okay. Well, if that's the case, what is this whole expression going to turn into? Moles. But you can't write moles. Why can't you write moles? Because they want these three values. They want these three variables. Again, this is crazy, and honestly, at this point, I wouldn't even know where to begin either. It's one of those weird things. But we know that if this is moles of MnO4, what goes on bottom? Moles of MnO4. And what's going to go on top? Moles of Fe2 plus. Well, where does a mole to mole come from? The coefficients. And if you look at the coefficients, it was 5/1. You could get this. This is easy. This is the part that I think would throw you off. I hope not. I'm just being honest with you. Yeah. Yeah. Now, this next part is easy. The mass of iron. Well, guess what? You've got moles. You can rewrite this whole entire thing and add what? Instead of stopping here, what can you do? No, well, I mean, yeah, you have to rewrite that and then add the molar mass. So that's part B, or part I. You have to add the mass. And then mass percent. See, that I'm just, yeah, it's the mass of, I'm just so confused at what they want. This is what they have for 3. Yes. No, I mean, I get them. I just don't know why they're asking for them this way. This is, yeah, times 100. So this.
Will it be in the compound?
Yeah. Exactly. This is part D, and you've already slammed A, B, and C, and so this is you're just holding on for dear life at this point. Applaud them and move on. Essentially applaud it, sir. That's the grams. Yeah, that's what they have is the total grams. All right, let's see if we can do E. Because remember, please don't give up. At least look at all the problems because they do that just to see if you'll give up and won't look at anything further. Okay. What effect will adding too much titrate have on the experimentally determined value of the mass percent of iron in the compound? What's going to happen? Too much volume? If you change this, what happens to your number of moles? It goes up. So the volume is too large. That means the mass should be too high. Because what are you doing across the top? You're multiplying. So if the volume goes up, what do all these numbers do? They all go up. So the mass will be too big. Again, that's one of those you got to know this. But if you ever increase volume, that should mess your mass up. Okay? Does that make sense? The official answer to E. The experimentally determined mass percent of iron in the compound will be too large because the volume is too large. It's
What effect will
adding too much titrate. You're adding volume. Okay? Because when it says adding too much titrate, that's adding volume. That's adding too much permanganate. Titrate is the permanganate ion. See ya. All right. Let's look at the matter of fact. Let me pause this video, and I'm gonna give y'all. Well, you know that's just gonna take too long. I'm not gonna do that. Hold that thought. All with drawing Lewis structures. Mr. Hand did it the second one, so he talked about how to draw the Lewis structures, and this was drawing for IF3. Now, he talked about how you figure it out. Now, how many valence electrons is that? 7. All right, F, how many is that? 7. There's how many of those? There's 3. So 21 plus 7 is 28. Okay. Now, what is the central one going to be? What? What element is going to be the central one? I. Now, so it's going to be I, and I'm just going to put F up here. I'm going to put F up here, and I'm going to put F down here. There's no rhyme or reason why I'm putting it there, but there's 3 of them, and what do you want to do them equally? Space them out equally. Right? Does that make sense? You want them as far apart as you can possibly do. Now, you always start with a bond between them, right? So how many does that give? That's 2, 4, 6. So that leaves you with how many? 22. Now, what was the next step? Nope. Fill them all the way around. So that's going to be 2, 4, 6, 8, 10, 12, 14, 16, 18. So 22 minus 18 is what? 4. So you have 2 extra sets, right? You with me? So you can have 2 here and 2 here. Why? Okay, here's the deal. Where else are they going to go? How? All the outer ones. No. So what happens here is that you have a problem as far as the internal one. Because what you do is you fill up all the outsides, and the central one gets all the extras. Yes, sir? You have to. That'll never happen. Yeah, that'll never happen. So you get this crazy looking thing, and what it's really going to look like and honestly, this is one I don't know of many teachers teaching because it's so funny looking. But that's really what it looks like. Okay? That's exactly what shape it is. It's a T shape. It legitimately is. Do what? It does. And that was what I was getting at. The next question was, on the basis of the electron dot, what is the shape? No, it really is. It really is T-shaped. Do y'all have that? It was the review pack, the review thing. It's in that. No. It's different than that. I keep losing that.
He was so happy about it.
I was thoroughly impressed, Elliot. It's in there.
I kind of thought it looked like that, you know.
All right, let me explain to you guys why it's the T shape. Do y'all have this? You may want to look at it. No, here's why. Let me show you what I'm talking about. Okay, listen. A, B, 3, E, 2. This is the generic formula. Let me explain how this works. All right, A is the central atom. What is the central atom? Thank you. It's I. So you have I. Do you agree with that? Now, B is the thing bonded to the central atom. What is B? F. And how many of them are there? There's 3. E is the funny part. E is extra pairs of electrons. How many extra pairs of electrons do you have? 2. So that's what this model is. And if you'll look, it doesn't say it on here, but it's what it is. Another way to explain it, but that's what it is. Do what? T-shaped. This literally is T-shaped. It literally is T-shaped. No, it's right there. Look. T-shaped. It's 1, 2, 3, and then 2 sets of electrons. It's on there. I promise. It's the extra pairs of electrons. I would write that down on there. AB3E2. And guys, I taught this year. I didn't get it last year. Again, okay? I really didn't. And so that's why I feel bad about it. But it really is T-shaped. Because I didn't get it last year. My apologies. Now, this one's even weirder. Okay? Joey. This one's even weirder. In the SO2 molecule, both of the bonds between sulfur and oxygen have the same length. Explain this observation, supporting explanation by drawing the Lewis electron dot or the diagrams for the SO2 molecule. So starting off with SO2, all right. So we have S, and then we have, first of all, S has how many valence electrons? 6. And there's O, and it has how many? 6, and there's how many? 2. So 2 times 6 is 12. 12 plus 6 is 18. So we know we have a bond here and a bond here. So how many is that total right there? 4. So minus 4 is 14. Now what do we do first? Fill up the outside. So 2, 4, 6, 8, 10, 12. So what does that give me left? That gives me 2. Well, what is the problem with that? The inside's off by 2. So we have 8. Do you agree we have 8 here? 8 here. But how many do we have here? 6. How many does it have to have? It's got to have 8. It's got to have what's that called? An octet. It's got to have 8. So what can we do with one of those red lines? We can do a double bond. Joey, here's your double bond. Now, here's the deal. Does it matter which one we take it from? No. So you can draw this 2 ways. Or you can draw it like this. Okay? And 1, 2, 3, and that right there. So it doesn't really matter. It's the right shape. So the shape is linear. I'll tell you what. No. It's not. It's actually bent. Let me explain why. Okay. Here. It's okay if you draw it like this. It's look. Please listen. It's A, B, 2, E. Why is that true? A is the center. There's 2 things bonded to it, and there's 1 extra set of electrons.
Linear can't.
That's not an extra set. That's
It is.
then what's up? No, never mind.
It's an extra set of electrons. Again, guys, I did a horrible job with this last year. That's why y'all are struggling through this, because I didn't teach it very well. I admit that. I did not do a good job with this. So, but the question says, why are they the same length? Well, what is longer, a double or a single bond? Single. Remember we talked about how single bonds, you get a little bit closer to double. Why are they the same length? Because they can go on either side. So what's going to happen is you're going to get this electrons shooting around like this. And so at any given point, the double bond will be here, and the next point, it'll be over here. So the bonds never have the ability to lengthen themselves. It keeps it pulled in. Does that make sense? So really, oxygen is more electronegative. So you're going to get a slightly negative pole here. But the deal is they're each pulling. So who's going to win the tug of war? Neither one. But what is that knot in the middle constantly doing? Going back and forth. So that's why the double bond can shift. So think of that being the center, the knot, and it's constantly going back and forth. Not necessarily, but it makes it a non-polar bond. Why is it non-polar? Because.
Is that with every bond?
Yep. You with me? Okay. So that's that one. Now, here's something I also did not teach last year because I didn't get it. It's okay. We all get it. Yeah, I know you're going to understand this. Right? SPD. No. the S. I know. I'm just writing this. I'm explaining it. Now there was each orbital can hold 2 electrons. So there was only one s orbital, right? Okay. There was how many p orbitals? Oh, 3. Remember, there's 6 elements. Each orbital can hold 2. So 6 divided by 2 is 3. Okay. D had how many orbitals? 5. Very good. So it's S1, P3, D5. Now here's the deal. How do you know the hybridization of this thing? It's based on what is attached to the center. How many elements are there and how many electron pairs are there, right? So that takes up the S, but how many S's can you only have? 1. Okay, so we're good there. So that checks off. And then you have P. So, but how many P's can you have? 3. And then you have that one. So that checks off. So it's SP2. Okay. All right, let's try this again. All right, let's try this again. So it's S O O. Why am I putting double lines there? There you go. Because I'm making it 8. I'm making that octet. So those can be interchanged, right? All right. So we know that the most it can possibly be if everything is full is like this. But it's based on how many elements you have present. Okay? The center one is always S. S for center. You're right. That makes total sense. Okay? Now, are we done with S? Yes. Well, how many more do you have? You have O. So what do you have to go to next? P. And then you have this one. You cross it off, but it's P what? 2. That's the hybridization. It's basically how many is bonded. Exactly.
Is it like rewriting your, if you had like another element, would you go to?
Yeah. If I had another, let me show you what we did earlier. We did what I. Okay. It would be this. Our I is the center, right? So that's S. What is F? That's P. Okay, but there's one more, so that would be 1. And that would be what? 3. SP3. That's it. That's all you have to do.
So it's like rewriting
It's rewriting it and telling me how many's there. That will be the hybridization of IF3. What? Just be SP. Why did you say chew? All right. So what? No. What would this be? All right. The center is S. So you got rid of that. And then there's 1, 2, 3. So that take care of the P3. And then what do you go to next? D. So SP3D. Sir. Bring it to me. Let me see it. No, I'm with you, Lane. Let's fix this. Okay, it's the S, and I'm just going to draw it one way. It's the. Come on. Or don't. All right, it's the S. All right, so you have 1, 2, 3. And then 1, 2, 1. Okay. It's the center is not the S. It's the number of bonds and extra electron pairs. So really, what I should have done is this is S. This is P. That's P2.
Okay.
Is that right?
No.
That has to be. No, I know what it is. It doesn't. Okay, I'm with you now. It doesn't matter. I'm working. It doesn't matter. That is one single bond. So that is P. So we're doing S. That's a P. And then this is also P because it's an extra pair of electrons. So it's sp2.
Okay.
Does it make a little bit more sense?
You have the extra valence on the orbital oxygen.
2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8.
He just did it wrong. It would have been.
But you have like 3 lines on that oxygen. You only have 2 lines on the oxygen to the right.
Okay, 2, 4, 6, 8. And then you move that one in for a double bond. You with me? Okay. So it's the double bonds don't matter. What were you doing? Okay. This one is let's see. I. Here, you really do want to see this though. While you're here, just get it. All right. So it's every bond an extra pair of electrons. So this would be S. This would be P, P, and P. So sp3 and then D. So the T shape, sp3d. It's bonds. It doesn't matter how many bonds you have present. If it's attached,
It's a matter of attached electron pairs.
it's attached, and then how many extra electron pairs you have. Bingo. That's exactly what it is. It's electron. Now, if there's but again, if it's a double bond, it doesn't matter. It's still an attachment point. It's an attachment point, not a bond. It's an attachment point, and this is an attachment point, so it counts as one single unit, which is one of these. Exactly. So if you look at, there was one. It was the last year it was I3. I think it was minus, and it was I. And let's see. That's this is. 1 times 3 is 20. Yeah, but it's 7 times 3 is 21, so it's 22. All right, so 22. So you get the bonds in the center. Okay, that takes away minus 4, which gives you 18. Fill up the outside, 2, 4, 6, 8, 10, 12. So minus 12 leaves you how many left? Leaves you 6, and they all go in the center. So 1, 2, 3, 4, 5, 6. This was the exact question on the exam last year. Okay? No, you can't.
But
Because there's 3, and everything else is full. Because
so can they have?
it can have more than 8. That's an expanded octet. So the hybridization of this would be, all right, that's a single, so that's S. Okay, and you have 1, 2, 3, so that's P, 3, and then you have 4, which is sp3d. This is technically a linear molecule. But how you would do this, it would be A, B, 2, E, 3. Is that on the sheet?
No, not A, B, E stuff.
I know. Okay. But what?
How would you know that it's not bent?
This is the crazy part. No, that just helps knowing the shapes. Let me show you this. Let me show it to you upside. Let me show it to you how they said it. Not upside down, but vertically. If we have I bonded to I, bonded to I, all these are full. All right. What they said is imagine it in the 3-dimensional world. Okay? Let's just say these are coming out at the board. These are kind of kicked back like that. And these are kind of kicked back like that. So one's sticking out, one's going that way, and one's going the other way. If you were to tie a string it would be essentially kind of like tying a string like this if we were looking at it from the top down. If this was in a tug of war, who would win? No one. Because all of the forces are equal going out and going back in. So what happens is this molecule stands straight up because they're pulling back and forth, so it stands it up into a linear molecule. How you know that? You got to be really good.
I mean, it makes sense.
It makes sense, but I would never have thought about that. No. And when I got the test back, I was like, well done, because I mean, this was a very, very missed question last year. People got the points for Lewis structure. I don't think they got the right shape. But the structure, I think you could have gotten based on how I've been doing it. The next question was the shape. Yeah, but see, and again, the hybridization.
If it was a bent, would you have to draw it in a bent or like?
Kind of like that.
Yeah.
But see, you would have seen that wouldn't have worked because electrons have to be as far apart as they can possibly be. They would be too close here and too far apart here. So you've got to think 3D, and I could see three-dimensionally like this, and I would have never gotten that. There's no way. But once I saw it, I was like, well, that makes sense. So, but I would have never have taught that ever because I would have never imagined that. So I don't know. I mean, even if it was F3 minus, it'd be the exact same thing. It'd still be linear because it has 22 electrons, and it's how it's balanced and standing up. Because one of the ones on the mock exam was what? XEF maybe? Because that's one of the ones I printed out. Or was it XEF5 maybe? What was it? Yeah, XEF4. Yeah, so XEF4. So xenon has 8 plus 7 times 4. So 28 plus 8, 36, right? Okay. So XE is going to go in the center. Now you can kind of figure this one out because there's 4. Yeah. Right? So you have F, 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 F. Okay. So 2, 4, 6, 8. So that's minus 8 gives us 28. Okay. I'm just write it up here. And then fill everything 1, 2, 3, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So 28 minus 24 is 4. So all you'd have to do is you'd have to put 2 here and here, which is exactly what it has.
And that's the expanded.
And that's the expanded octet. And how would you do the hybridization? All right, so that is S, 1, 2, 3. That's P3, and then D2. And that shape
Is square planar.
square planar. Yeah, something. No. Yeah. No, matter of fact, because the one that says what is the hybridization of this? SP3D2, which is exactly what we got. The other one.
See, if we would have had the workshop or whatever.
Yeah. And I think if people will watch this, I think they'll figure this out. Again, this is 8, and then 6 times 3 is 18. 8. Yeah. Because there's 6 valence of oxygen. 18 plus 8. Yeah, 26. All right. So there's X, E. I'm just going to draw it like this, and you have O, O, O. So that's 2, 4, 6. So minus 6 equals 20. Fill it all the way up. 2, 4, 6, 8, 10, 12, 14, 16, 18. So minus 18 leaves you 2. 2, 4, 6, 8. And you're done. Hybridization. You would have S, P3. And this is just like NH3, and that's trigonal pyramidal. Pyramidal, because this right here kicks all these down at an angle. Yeah. So that's how, if y'all will follow this, y'all can draw any of those little structures. You can draw any of those little structures. And I've just learned this. I didn't know this until this year when I went to something. And when he was drawing on the board, it started clicking with me again. Okay. Well, I feel better. Hope if again people watch this, they'll figure it out. Thank you.